We learned that substitution is a powerful method for trying to find antiderivatives, and here we're going to combine it with the fundamental theorem of calculus to evaluate definite integrals. So here's our definite integral, from minus 2 to 2, x times x squared plus 4 to the 7th. The fact that I have this parenthetical expression with an x squared and its derivative essentially on the outside means that this is a prime candidate for substitution. So how does this work when you're doing definite integrals? Well, it's basically the same thing, but there are a couple changes having to do with the limits of integration. So let's do substitution. The substitution we'll make is u is equal to x squared plus 4. In that case, du is going to be 2x dx. And I'm looking for to substitute these things in. So for the u, I put that here. I get u to the 7th. And then the x dx, what is that over here? Well, that's almost the same as what I have over here, except there's a 2. So I'm going to divide both sides by 2 in this expression. I get du over 2. So x dx, what's left over is du over 2. Okay? Now I write this integral sign. Now to be fair, this minus 2 and this 3 are hooked up with the variable x. If I want to rewrite the limits of integration here, I'm going to have to change from the x variable to the u variable. In particular, by this expression, if x is equal to minus 2, then that implies that u is equal to minus 2 squared plus 4, which is 8. So a minus 2 here corresponds to a u being 8. Similarly, an x equals 3, that upper limit of integration, now becomes a u equal to 3 squared, plus 4, which is the same as 9 plus 4, which is equal to 13. So in terms of the u variable, the limits of integration are different. They're now 8 and 13, whereas they used to be minus 2 and 3. Okay, nonetheless, this integral is now equal to this integral, and I can now use the power rule, the inverse power rule, to solve this. So I get u to the 8th over 8, and then I have a 2 there, so I don't forget that 2. And then I write, now that I finished finding the antiderivative, I use 8 and 13 with this bar, just as before, to indicate that I'm going to plug in these values. I'm applying the fundamental theorem of calculus here. So this can be 13 to the 8 over, well, 2 times 8 is 16. So that's plugging in 13. Now I'm going to subtract off plugging in the 8. So I have 8 to the 8th divided by 16. Okay, and then you could simplify this if you want, or probably use your calculator to estimate. But this is your answer, right? So there's your answer. So again, the first step was to make the substitution, but it's a little more complicated because you may want to change the limits of integration. If you do change the limits of integration, you have to do it using this formula, as we did right here. There's an alternate way. If you don't like changing limits of integration, there's an alternate way to do this, and let me sketch that. Okay, same problem. I'm just going to do things a little differently. Okay, I'm going to make the substitution as before. U is equal to x squared plus 4, and du is going to be 2x dx. And as before, x dx is going to be the same as du over 2. So when I make the substitution, x squared plus 4 to the 7th becomes u to the 7th. X dx becomes du over 2. But what I'm going to do here is I'm going to leave the limits of integration blank because I don't want to go through the hassle of having to change the limits of integration, and we'll see what to do later with those limits of integration. Now I take the antiderivative, just as before. I get u to the 8th divided by 8, and then I also have this 2 remaining from the du over 2, and then I write these little stars because I didn't figure out what those were. And now, instead of figuring out what those stars are, I'm going to change back into the x variable where I know what they are. So I'm going to resubstitute u equals x squared plus 4. This is much like what we did when we introduced substitution as a method in the first place. 2 times 8 is 16. And now I'm going to have, since I've changed back to the x variable, I can rewrite the original variables here. And now I can plug in, and I can plug in the 3, and so I get 3 squared plus 4 to the 8th over 16. And then I subtract, and I plug in the minus 2, so that's minus 2 squared plus 4 to the 8th divided by 16. And then you can solve for these, so 3 squared plus is 9 plus 4 is 13 to the 8th, right? So I'm going up this way, divided by 16, minus, and then minus 2 squared is 4 plus 4 is 8 to the 8th over 16. Okay, so that's a different way. Notice it's the exact same answers I got before, but it's a slightly different way. There I didn't have to change. I waited to the last minute to change into my my limits of integration. I just plugged in the minus 2 and the 3. Okay, that's two different ways of using substitution to compute definite integrals.